Hello class, welcome back. Today we want to study gases. Gas molecules are constantly in motion. As they move and strike a surface, they push on that surface. It means they apply some force on the surface. For example, look at these gas molecules, they are the green, and this is the surface, you see. As they hit the surface, they apply force. If we could measure the total amount of force exerted by gas molecules hitting the entire surface at any one instant, we could know the pressure the gas is exerting on that surface. Because pressure equals to force per unit area. Mathematically, this is how we write it. What is the effect of gas pressure? The pressure exerted by a gas can cause some amazing and startling effects. Yes. Whenever there is a pressure difference, a gas will flow from area of high pressure to area of low pressure. So whenever there is that difference, gas tend to move. They are always moving. They'll move from area of high pressure to area of low pressure. And the bigger the difference in pressure, the stronger the flow of the gas. So the bigger this difference in that pressure, the stronger the flow of the gas. So difference in air pressure result in weather and wind patterns. So the weather and wind patterns that we have in nature are usually due to difference in air pressures. The higher we go in the atmosphere, or you climb higher, the lower the atmospheric pressure. So rapid changes in atmospheric pressure may cause our ears to pop due to imbalance in pressure on either side of the eardrum. We can see it this way. So this is our eardrum. You see how it is. You have the inner part here and the outer part. So if the pressure of air here is not balanced to that, it's not equal, not the same, that's when you have that pop. So what instrument do we use in measuring pressure? Barometer. A barometer is a column of mercury separated by air pressure. So you see, this is a column of mercury. This is our dish that has mercury. And you have the mercury, is in the tube. But as atmospheric pressure pushes the mercury here, of course, it climbs here, but there is some kind of a difference. So what happens is that if you fill this tube with mercury, then you invert it and put it on a dish that contains mercury. The mercury will push base, they will come down, the gravity will pull it down to match the atmospheric pressure. So here, you don't have anything, it's a vacuum, because the tube was full at the beginning. But because of the pressure, it has to match the atmospheric pressure. So it comes down, and here you have a vacuum. There's nothing there, there's no air, there's nothing. And this distance from here to here is what matches the atmospheric pressure. So the column of mercury supported by air pressure, force of the air on the surface of the mercury balanced by the pull of gravity on the column of the mercury. So that's what you see. So this 760 millimeters mercury, or 29.92 inch, is equals to 1 atmosphere. So that is a barometer. We want to look at some common units of pressure. Atmosphere, Pascal, millimeters mercury, inches mercury, torr, pounds per square inch. Pounds per square inch. And this is N, this is Newton. Newton is kilogram per meters per, kilograms times meter per second square. So 1 atmosphere equals to 101,325 Pascal. 1 atmosphere equals to 14.7 pounds per square inch. 1 atmosphere equals to 29.92 inch mercury. 1 atmosphere equals to 760 millimeters mercury. 1 atmosphere equals to 760 torr. So 1 millimeters mercury equals to 1 torr. Let's try and solve some problem. A high-performance bicycle tire has a pressure of 182 pounds per square inch. What is the pressure in millimeters mercury? So if you notice, all our conversions were to atmosphere. So what you have to do, you have to convert pounds per square inch to atmosphere, then to millimeters mercury. So that's it. Pounds per square inch to atmosphere to millimeters mercury. We need conversion factors. So we'll have the conversion factors from pounds per square inch to atmosphere, then from atmosphere to millimeters mercury. So conversion factors, very important. Make sure you learn how to write them. So that's it. This is to convert to atmosphere, and this is to convert atmosphere to millimeters mercury. So let's arrange it. So this is 182 pounds per square inch times the conversion factor to convert to atmosphere. Cancel pounds per square inch, then you multiply it by the conversion factor to convert atmosphere to millimeters mercury. So our answer is 6.82 times 10 to the third power millimeter mercury. Please, significant figure, very, very important. Make sure you know how to report your answer in the correct significant figure. Our answer should be in 3 significant figures. This is exact number. This is exact number. Exact numbers do not detect the significant figure, the answer of the significant figure of your answer. That's why our answer is in 3 significant figures. Let's take this example. So convert 98128 Pascal to pounds per square inch. They're giving us the relationship to get the conversion factor. So what you need to do is 98128 Pascal. Then you convert it to atmosphere. So 1 atmosphere. One atmosphere all over 101,325 Pascal times, now you have 14.7 psi all over 1 atmosphere. This is equals to cancel Pascal, cancel atmosphere. You have to report your answer in 1, 2, 3, 4, 5 significant figures. So let's go to our calculators. Go to your calculator, take your calculator and do the calculation. So 98128 times 1 times 14.7 divided by 101,325. Your answer is 14.236 psi. So that should be your answer in 5 significant figures. Now I want to look at some gas laws. The gas law. The movement of gas molecules can be affected by volume. In small volumes, the gas molecules tend to heat the container more. Can be affected by temperature. Increasing temperature increases the motion of the gas molecules. Can be affected by number of moles, number of particles of gas molecules, which we represent as N. So let's look at Boyle's law. Boyle's law states that pressure of a gas is inversely proportional to its volume. At constant temperature and constant amount of gas. So it says that as pressure increases, the volume decreases. But the temperature is constant and the amount of gas is constant. Take note of that. So mathematically we can write it as P times V equals to constant. So P times V is equal to constant. P2 times V2 equals to constant. So you have two constants. So this is equal to this. Therefore, P1 times V1 equals to P2 times V2. So this is Boyle's law. So let's look at it. If we were to carry out an experiment in the lab. So this is our gas in this tube. You see the height here. But as we keep putting mercury, you see, because gases are compressible, you see, we are compressing the gas, and the height of our mercury is increasing. So let's look at it. So length of air in the column before you started putting the mercury, that's it. As you're putting it, the gas is compressing. So if the length was 48 inch, that was 0, you have not put any mercury. So as you keep putting mercury, see, the column of the which the air is occupying is decreasing, and the column in which the mercury is occupying is increasing. So we are adding mercury to the J tube with our air trapped inside. The length of the air column is used to measure the volume of the gas. So if you carry out that experiment, we'll notice that as pressure increases, the volume is decreasing. So that is Boyle's law. As the pressure is increasing, the volume is decreasing. So inversely, inverse volume versus pressure of the air is a straight line. So this is an experiment carried. So pressure, you see, as the pressure is increasing, the volume is increasing. So, but P times V is constant, just like this. It's a constant. So we can even experience it here. Pressure is caused by molecules striking the side of the container. When you decrease the volume of the container with the same number of molecules in the container, more molecules will hit the wall at the same instant. And that will result in increase in pressure. Let's try to apply Boyle's law with people who are diving. So this is a diver. He is just at the surface of the water. The depth is 0 meters and the pressure is 1 atmosphere, still at the surface. Since water is more dense than air, for each 10 meters you dive below the surface, the pressure on your lungs increases by 1 atmosphere. So at 20 meters, the total pressure is 3 atmosphere. So if your tank contains air at 1 atmosphere pressure, you will not be able to inhale it into your lungs. So scuba tanks have a regulator so that the air from the tank is delivered at the same pressure as the water surrounding you. This allows you to take in air even when the outside pressure is large. So if a diver holds her breath and rises to the surface quickly, the outside pressure drops to 1 atmosphere. According to Boyle's law, what would happen to the volume of the air in the lung? Of course, it will increase immediately. So since the pressure is decreasing by a factor of 3, since the pressure is increasing by a factor of 3, causing damage to internal organ. So always inhale when rising in case you're diving. So let's do some problem. Let's look at some problems, some examples here. A cylinder with a movable piston has a volume of 7.25 liters at 4.52 atmosphere. What is the volume at 1.21 atmosphere? So V1 is 7.25, P1 is 4.52, V2 we don't know, but P2 is 1.21. 1.21. So we want V2. So this is our equation. P1 times V1 equals to P2 times V2. So we rearrange it to get V2. It becomes V1 equals to P1 times V1 over P2. So we already have everything up there. All what we need to do is to substitute. So this is our P1. This is our V1. And this is our P2. When we do this calculation, our answer is 27.1 liters. 3 significant figures. But you know, when you do it in a calculator, when you calculate it, let's see what we are going to get. So we are calculating 4.52 times 7.25 divided by 1.21. So I'll just show you the figures I got from the calculator. 7.08264463 liters. Please, you cannot report this. That's why we did significant figures. So our answer must be in 3 significant figures. So what do? This figure from the calculator is supposed to end here. So look at this number. Since it is more than 5, change it to 1, add it here. That is why we have this answer. You must report your answers in the correct significant figures. We want to look at Charles' law. Charles' law states that volume is directly proportional to temperature, but pressure and number of particles must be constant. This is N. So temperature increases, volume also increases. So the graph of volume versus temperature is a straight line graph. So V equals to constant times T. Our T is in Kelvin. So this is our Boyle's law equation. We can see the graphs of different gases. So we can see the graph. So if we plot different gases, this is the same gas, oxygen, but under different pressures. So it's the same oxygen, 1 gram of oxygen at 1500 Thor, 1 gram of oxygen at 2500 Thor, 0.5 gram of oxygen at 1500 Thor, 0.5 gram of, all of them gave a straight line graph. And when this is extrapolated to 0 volume, this temperature here is 273. Okay, minus 273.15. And we call this the absolute zero temperature. So you see, is the absolute, all of them is the absolute zero temperature. Minus 273.115 degrees Celsius. So the pressure of a gas inside and outside the balloon are the same. But at low temperatures, the gas molecules are not moving as fast, so they don't hit the sides of the balloon as hard. Therefore, the volume is small. So kinetic energy, so that's kinetic energy, this is ice. So the volume becomes small because the particles are not moving as much as they are supposed to move because the temperature is cold. So it makes the balloon to shrink. So the pressure of the gas inside and outside the balloon are the same. But this time at higher temperature, the gas molecules are moving very fast, so they hit the sides of the balloon harder and frequently, causing the volume to become larger. So let's do some example. Let's do some, try some examples here. A gas has a volume of 257 liters at 0.0 degrees Celsius. What was the temperature at 2.80 liters? So this is what we got. V1 equals to 2.57 liters. V2 is 2.80 liters. T2 is 0 degrees Celsius. So we want the temperature. We want T1 in degrees Celsius. Then we can convert it to Kelvin. So get it in, it's given in degrees Celsius, so you have to convert it to Kelvin, please, because our calculations are in Kelvin, not in degrees Celsius. So this is our equation. And to convert to Kelvin is degrees Celsius plus 273.15. So this is the equation to convert temperature from degrees Celsius to Kelvin. So we rearrange our equation. Then now we solve. So when we solve, so this is our T2. This is our V1. This is our V2. So you notice that our temperature is 297.6 Kelvin. We have to convert it back to degrees Celsius. So to convert it, Kelvin minus 273.15 gives you our temperature in degrees Celsius. So we solve the problem in Kelvin, convert it back to degrees Celsius. But your calculations, please, for gas law, it should be in Kelvin. Temperature should be in Kelvin, not in degrees Celsius. You must convert degrees Celsius to Kelvin to do this calculation in gases before you reconvert it back. Now I want to look at another law, Avogadro's law. It states that volume is directly proportional to the number of gas molecules. So this is the equation. V1 over N1 equals to V2 over N2. So as amount of gas increases, the volume increases. So V equals to constant times M. The P and T must be constant. They cannot vary. And the number of gas molecules, we are counting it in moles, please. N is moles. So equal volume of gases contain equal number of molecules. The gas does not matter, whether it's oxygen, whether it's carbon dioxide, whether it's hydrogen chloride gas, sulfur dioxide. The gas does not matter. Equal volume of gases contain equal number of molecules. So let's try to do some example of Avogadro's number. A 0.225 mole sample of helium has a volume of 4.65 liters. How many moles must be added to give 6.48 liters? So our V1 is 4.65 liters. Our V2 is 6.48 liters. Our N is 0.225 moles. That's N1. We want N2. And the added moles, because we need to get the N2 before we know how much was added. So V1, V2, N1, we have it, but we don't have N2. So to get the added number of moles, we have to find N2 first, then we'll subtract N1 from N2 to get the added number of moles. So this is our equation to find N2. So let's do our substitution and solve for N2. So this is N1 times V2 all over V1. So that's our N1. This is our V2 and this is our V1. When we do that calculation, our answer is 0.314 moles. 3 significant figures, that's your answer. If you put in the calculator, you will not get this. So you have to round it off or up. So to get the added number of moles, it's just N2 minus N1. And what was added was 0.089 moles. We'll take another example here. If 1 mole of a gas occupies 2.4 liters at STP, standard temperature and pressure, what volume would 0.75 moles occupy? So STP, standard temperature and pressure. So what is our standard temperature? Our standard temperature is 25 degrees Celsius. What is our standard pressure? Is 1 atmosphere. Take note. So this is standard temperature and pressure. Our standard temperature is 25 degrees Celsius. Our standard pressure is 1 atmosphere. And they say the volume that we have is this. So if we have to solve this, it said 1 mole of gas occupies 2.4 liters at standard temperature and pressure. What volume would 0.75 moles occupy? So we have V1 over T1. No, So let's see. We have a N1 over V1 equals to N2 over V2. So our N1 is 1 mole. Our V1 equals to 22.4 liters. Our N2 equals to 0.750 moles. Our V2, we don't know. So let's try and solve. We're going to rearrange this equation. V2 equals to N2 times V1 over N1. So this is 0.75 moles times 22.4 liters all over 1.00 moles. So our V2 equals to 0.75 times 22.4. So our volume V2 is 16.8 liters. So that's the volume. Please make sure you practice these calculations. Try to look at them and solve them. So we are going to continue with this class.